got tests next week or not?
We did 2 today.
2 today?
Yeah.
Power
and controls.
How many had a test today? I congratulate you showing up.
Analogs Monday.
Analog test Monday.
Analog Monday?
Yeah.
Alright, go ahead. Go ahead.
600 megahertz uniform plane wave, incident in the z direction on a thick slab of Teflon, epsilon relative equals 2.1, mu relative equals 1.0, imparts a 1 volt per meter amplitude, Y polarized electric field intensity at the surface.
So you got one, the E field is 1 volt per meter? Per meter at here, okay, so this is the knock. Go ahead.
Assuming conductivity equals 0 for Teflon, find Teflon E of CT.
That's an E field he gives us, right?
He gives us the amplitude of the E
He wants the E field,
He wants the E field as functions of distance and time.
right, he wants beta. So for this, what he's looking for is this equation. He wants E expressed as some E naught. And since it's lossless, it's going to be just a cosine of omega t minus beta z in the AY direction. It's propagating the Z direction?
Yeah.
You all follow me with this? I'm sorry, which question is this?
This is 6.27.
All right, now here he's telling you the field is in the material. He gives you the material. He gives you the frequency, and he wants you to express it in terms of the standard form, cosinusoidal form. He doesn't say anything about a phase change. So the things, 2 things you need, if it's just the E field, you need beta, right? And there is no alpha for this one. So frankly, omega is just 2 pi f, right? So that's going to be 2 pi times 600 megahertz, or it's, I'll put it this way, times 600 times 10 to the 6. Then you need beta. Well, since it's lossless, technically the propagation constant is alpha plus j beta. In this case, it's going to be the square root of j omega mu, sigma 0, so it's times j omega epsilon. That means this is just going to be j omega, then it's going to be times square root of mu epsilon. And the easiest way to do this, you'll notice that that's going to be strictly imaginary. That's strictly imaginary. Beta, therefore, is equal to omega times square root of mu epsilon. That's omega over c, because it would be the square root of mu naught epsilon naught, times the square root of epsilon relative. Y'all follow me what I'm doing here? Can you read it in the back, guys? All right, how many see what I'm doing? All right, I'm trying to be clear about this. There's the propagation constant, alpha is 0. This is beta. Mu epsilon is square root of mu naught epsilon naught times the square root of mu relative epsilon relative. Well, the square root of mu naught epsilon naught is 1 over c. So I put it like this. And that makes this equal to, since that's omega, 2 pi times 600 times 10 to the 6 over c is 3 times 10 to the 8. And it's the square root of, what is it, 2.1. You can tell me what that is, but that's 6 times 10 to the 8th over 3 times 10 to the 8th, that's 2. So it's really 4 pi times square root of 2.1. And can anybody give that to me? Like, I don't know.
18.23.
And that would be radians per meter. Y'all follow me on that, class? That's beta. We've got the equation. The only thing we can write it down, this would be just 1, and it's cosine of omega, which is, I'll put it that way, 2 pi times 600, 10 to the 6 t minus, and this is going to be 18.23, in the Z direction, AY. Is there any other part to that?
Yeah, he asked for the H field in the same form and also the average power.
Okay, all legitimate questions. So for the H field itself, we'll do that here. We know the H field, we could do this a couple different ways. I could put the E field in terms of a phasor, right? You all agree with that? Might as well do this. If this is the E field in the time domain, in the phasor form, it would still have same magnitude, right? And then it would just be times e to the minus j beta z in the AY direction. Y'all agree with that? Can y'all read it back there? My handwriting's a little questionable at times. All right, if that's the E field and I want the H field in the phasor domain, remember how we get it? H is equal to what? H is 1 over eta, so now we have to get eta. Unit vector in the direction of propagation crossed into the E field. Do y'all remember that? Phasor form? How many do? All right, it's good to know this because this is a shortcut. If they're plane wave propagations, you can get E from H, H from E very easily from those little tricks. So we need eta for that to work. We'll get it here. What is the general form for eta? You should always know that. Square root of j omega mu, right, over sigma plus j omega epsilon. That's the general form, right? Here we have sigma 0, correct? Therefore, eta in our case becomes simply square root of mu over epsilon. Do you all agree with that? Y'all with me on this? Okay. Now I'll break that out as the square root of mu naught over epsilon naught times the square root of mu relative, which is 1 over epsilon relative. Now, that means eta is equal to, well, why did I do this anyway? What is the square root of mu naught over epsilon naught? No, it's eta naught, isn't it? 120 pi. You guys said it. Y'all agree with me? That's the reason I did it this way. So it's 120 pi. And then I simply have divide this by the square root of 2.1 because epsilon relative is 2.1 and mu relative is 1. Can anybody give that to me? I don't know.
It should be 3.8.
Huh?
I think it should be 3.8.
120 pi. No way. Over 2 square root of 2.1? That sounds.
I got 260.
Yeah, 260, I'm sorry.
260, yeah. 260 sounds about right. Almost. All right, now we can get H over here, and I want to write this down. By the way, just from the unit vector in the direction of propagation is what, guys? Say it again. I can't. AZ, right? Positive AZ. So now we can go through this. We can leave it as 1 over eta, and I'll just leave it as eta. And then it's AZ crossed into the E field. That's the E field, which is E naught, e to the minus j beta z in the AY direction. Okay? That means this is the phasor form. It's going to be what? Magnitude is going to be E naught over eta. Most of you knew that already. It'll have e to the minus j beta z. We've got beta. And what is AZ crossed AY? AZ crossed AY is minus AX, right? Minus AX. So I'll put the minus sign here in AX direction. Y'all agree with me? We'll do it this way. Okay? Now, we've got that. That's phasor, right? We might as well put a number down here. What is 1 over eta naught? Small for starters. One over 260.
0.00384.
Is that right, guys? All right, so that's the magnitude. It's got e to the minus j. We know what beta is there, z, in the AX direction. Now if I want to get the H field in the time domain, I take the real part of e to the j omega t times the H field phasor form. I'm just gonna leave this H vector phasor here. I'm putting it down for completeness. This is how you do it technically. But we know one thing that's gonna happen, right? When I multiply by e to the j omega t, I'm going to get effectively something that's got a cosine and a sine term in there, both varying as omega t. And because h has got e to the minus j beta z in there, that gets sucked into the cosine of omega t arguments too. So it's cosine of omega t minus beta z. The real part is just the cosine, meaning this becomes minus 0.0384. Then it's going to be times cosine of omega, right there, 2 pi times 600 times 10 to the 6 t minus beta, which is 18.23. And this is going to be in the AX direction. Now, there's nothing magic here, it's just turning the crank, you might say. But I have a question for you and a comment too. If I didn't want that negative sign there, what might I do inside this argument? Anyway. You can add or subtract pi, or 180 degrees. Do y'all follow me on that? And then you could erase that if you wanted. You can leave it there too. Either answer is absolutely correct, mathematically. It's exact. All right, that's the time domain form of the H field. Now, if they want the average power, we'll do it here. So it's lossless, right? In general, average power is equal to 1/2, right? Magnitude of the E field squared over magnitude of eta, right? E to the minus 2 alpha z. Then you're going to have cosine of the angle associated with eta, and it would be in the direction of propagation, which would be AZ. Do y'all follow me on that, class? That would be watts per meter squared. I can put the units. That's the general form. In our case, what do we know? Well, we know it's 1/2, gotta have that, right? We know the E field is 1 volt, right? So don't even need to worry about that. Eta, you gave me, was it 260? 260. All right, what is alpha? 0. There's no exponential damping. And what's the angle associated with eta? If it's strict real, what's the angle?
0.
There's no J component to that, right? So it's just 0. What's the cosine of 0? 1. You don't need that. And this would be in the AZ direction. And that would be, since it's 1, that would be watts per meter squared. Can you just give me that number? So it's 1 over 2 times 260. So it's half that value, 0.380. Huh?
It's like 1.92 milliwatts per meter squared.
Does that jive with the book?
Mm-hmm.
All right, that's the problem in a nutshell. If anything changed, if there was a value of mu relative that was different, then you would adjust beta accordingly, and you'd have to adjust eta accordingly from the fundamental formulas, right? If it was lossy, if sigma had a non-zero value, then you would have a value for alpha here, and eta would be affected as well. Y'all follow me? And beta, but as long as you know the fundamental formulas, you can't go wrong. And most of them, if it's lossless, just reduce to some very simple, straightforward equations. Other questions? Good question. If you all had tests, somebody surely has a lingering question. No? Nothing? Maybe you're exhausted. That could be. Okay. Well, I want you to know we're ahead of where we need to be. We're basically, most of the material Matter of fact, all of the material that's needed to be covered in this course has been covered. And that's good, but you're getting, and I don't know if I'm teaching EMAG too. I'm just gonna level with you. I have no idea what I'm teaching in the fall. Did they happen, anybody take a peek to see if?
Yeah, it says you're EMAG too.
All right, fantastic. That is super, because we can pick up where we left off. And, which is good. So I want to talk to you about two things today. The first has to do with something very important when it comes to detecting targets using radar and any other sensor things. It's called polarization of a wave. And the second is reflection from surfaces. Now, the reflection from surfaces is something that parallels transmission line stuff you've had before, but polarization is something you haven't had. So let me just tell you what's going on and why it's important. If you have an electric field and it's only polarized, meaning it only has a vector direction, say in the AX direction, but it's propagating in Z, then if you would take a look at a point in space versus time of the E field, it would start at 0, it would grow in a direction, become a maximum, then it would come down to 0 again, and reverse its polarity, it would go negative. Do y'all follow me? So the waveform would look like this. The tip of the wave would be going from a relative minimum 0, this is at a point in space, to a maximum, back to 0, again down. And if you actually traced out the tip of that electric field, it would be a straight line. Can you all envision that? Now, if it was in this direction, if the polarization was in the Y direction, it was propagating that way, then it would trace out a line like that. Do y'all follow me? Now, if you have, this isn't exactly true, but if you had an electric field component in this direction, superimposed on electric field component in this direction, and they both had the same cosine variation, then you would have an electric field tip that would go like this. Do y'all follow me on that? You would have a slant. If you change the phase by 90 degrees of one of these, if the electric field in the vertical direction, let's say the same magnitude, and the electric field in the horizontal direction were now off by 90 degrees, then what happens is the tip's value of that electric field will always be the same. It will just rotate in time. Y'all follow me on that? If you're at the same point in space, the only thing that would change would be the vector direction. The magnitude would be the same, which means the average power would be the instantaneous power. It would be constant. And here's the real thing about that. When you have a wave, and it's called circular polarization, now the tip of that waveform is basically just going to corkscrew around. If you froze time and looked at space, but when you have a wave propagating with right-hand circular polarization, now I'm going to explain this briefly and I'll do it again. Right-hand circular polarization means you take your right hand and you put your index finger in the direction of the electric field and your thumb in the direction of propagation. All right? And if the thing, this is right-hand circular polarization, if the thing does this, goes clockwise, that's right-hand circular polarization. Now don't get hung up on right or left. Left hand would be, as you might guess, you put your left hand in the direction of propagation, and if it corkscrews this way, it's left-hand circular polarization. Do y'all follow me? Don't worry that much about the type. However, here's what's important. If you send out a waveform that's got right-hand circular polarization at a given frequency, and it hits a target, a conducting target, the reflected pulse has left-hand circular polarization. It's exactly opposite. Now what that enables you to do with the use of filtering, if you send out right-hand circular polarized waves, you can get a lot of different things back, all right? All sorts. You can have electromagnetic interference, you can have people trying to jam you, but you can get rid of all that other stuff and only look for left-hand circular polarized waves at that frequency and then do processing to see how long the echo took to get back to you so you can get the range. And you can actually get the Doppler shift from this stuff. You can get all the information you need. So that's the benefit of using a polarized wave, not linear, but circular polarized or elliptical. Now here's the thing about elliptical polarization. As you might guess, an elliptically polarized wave, the tip just traces out an ellipse. That's all it does. Now, if you're involved with weather radar, which is getting to be very important. We live in Alabama, we get hit by bad weather all the time. Then the meteorologists have found out that there are basically three types of precipitants. There's rain, which is a long teardrop shaped, really, droplet. Then there are things called graupel that is like slush. All right? It's part water, part ice, it's slush, but it's called graupel. Then there is ice. All of them have very unique shapes, well, at least statistically unique, and they all can, you can also differentiate what's there by using the type of polarization. If you use elliptical polarization, where the ellipse would be in this direction, and rain is falling, it will have the strongest return when the droplet is aligned with the major axis of the elliptically polarized wave. Now, I'm not going to go through all the method. However, if rain's falling at this angle, then you would get a maximum return, reflectivity, when the elliptical polarization was aligned with that. Now, why is that important? Because that will tell you how the thing's actually moving in the wind field. And Doppler shift will give you the actual velocity of really the precipitant in your direction. That's really important. Have you heard of something called, and down here, it's a weather radar, but they look for a hook echo using Doppler radar. Have you heard of this or not? No? How many have? I'm just curious if anybody has. Nobody?
I think so.
Have you heard the term Doppler weather radar?
Yeah.
All right. They're looking at the velocity field of these particles. They're trying to get the velocities of these things because they know something about tornadoes. They have what's called a hook echo, and they have a very clear velocity differential signature. If you could actually track the particles versus altitude, they can pretty much tell you when there's a real tornado based on that and the type of particles, which is kind of interesting in reflectivity. So that's one of the big interests with weather radar. The other is obviously trying to locate targets, and that's the reason polarization is so important. There's other reasons for it, but those are the ones I'm real familiar with. So what am I talking about when I say polarization? In your book, he's going to start talking about polarization on page 347. And so if we think about polarization in general, the way I expressed it, if this is X and this is Y, and Z's coming out of the board, and we have a wave propagating in that direction, we have two basic components. We have something in the X direction, something in the Y direction. And the superposition of these two at any time would be the waveform. Y'all follow me? So really, what you would have is an electric field like this with some angle, tilt angle. Don't worry about that. The tip here is going to trace out some shape. It's either going to be elliptical or circular or a straight line, linear. You all follow me? It's only three possibilities. So the electric field in the X direction has some magnitude. I'm just going to call it E naught. We can have it cosine of omega t minus beta z, and it's in the AX direction. The E field in the Y direction will sum E naught 2. I'm just going to leave it at both as E naught. And it'll be cosine of omega t minus beta z, but then it can have a phase angle. And it can be either plus or minus some phase angle, AY. Y'all follow me on what I've done here? These are just general description of propagation. So when we talk about polarization and how we're going to analyze this and understand it, just set z equal to 0. The reason is it doesn't matter what value z is. That value only complicates things. So now these waveforms break down to simply EX. This is with z equals 0. The sum E naught cosine of omega t AX and EY is equal to some E naught cosine of omega t minus some phase angle. Alright, so those two descriptions hold true for a plane wave propagation at z equals 0. With me? Now, let's take a look at what happens. We're going to assume, for the sake of simplicity, E naught is the same in both, and I'll just call it 1 volt per meter. And now we're going to let the phase angle be 0. So if that's the case, if the phase angle is 0, I have two identical equations in every way. Do you all agree with this? Can you see if you were to get the trace of that, this is x and this is y, the trace would be, well, you can start plotting these. If the phase angle is 0, just take a look at this. Let omega t equal 0, what do you get? Cosine of 0 is 1, right? I get, both of these things start at a value of E naught. So if this is, call it EX, not the x-axis, call this EY. Both of them start at, over here at E naught. And you can see that this would be the first point. That would be where the electric field position would be, superposition of those two. Do you all agree with that, class? All right, now let time go by. Now let's let omega t be equal to 45 degrees. With me? So if omega t is 45 degrees, this is the way you do this. You plot a few points and you can figure out the line. This is the simplest thing. So if omega t is 45 degrees, cosine of 45 is 1 over square root of 2. It's about 0.707, 70% that value. So the next point is down here at 0.7 about E naught. Here it's 0.7 E naught. Or it's right here. You all see that? You can connect those 2 points, and we know the next point is going to be in a line that connects the two if you extend it. So here's the trace of that. That's all you care about. That's linear polarization, and we could figure, quote, tilt angle if you want it. That tilt angle doesn't really amount to much, but not for you guys. It has to do more with remote sensing. That would be the tilt angle right here. By the way, what would this tilt angle be? Just looking. How many say it's 45, right? Now notice it's going from the upper right corner to the lower left corner. If all of a sudden, we wanted to take a look at what happens when I do this, when I let the phase angle here be pi, or 180 degrees. Do y'all follow me? With me? So if this is 180 degrees, so that was in EY, right? So I'll call it plus, it won't matter, plus or minus pi. Now what did I tell you about if you add plus or minus pi inside this? What can you do instead of putting a pi there? I can get rid of that pi and just put a minus here, right? So now if you plot that one, what happens? Well, do the same thing that we did before. Start with omega t, the argument of the cosine being 0. When it's 0, the cosine of 0 is 1. I get E naught for the x distance, right? So it comes out E naught here. What do I get for the y distance? Minus E naught, right? Now it's down here. And here's my first point. How many want to take a shot, or who wants to guess the next point? If omega t is 45, or pi. It's going to be same as what was up here, only mirrored down here. It's going to be right here, isn't it, class? And you can see now this one goes from upper left to lower right. Y'all follow me? Those are the two possibilities for linear polarization when you're talking about same magnitude fields. Right? You can also have linear polarization and just get rid of EY altogether. Now you have something that's a straight line, but it's only x polarized. Or vice versa, get rid of that. These are just mathematical ways of describing different types of electric fields and polarization for plane waves. And not a big deal. And I don't worry about tilt angle and stuff like that. Doesn't matter. So now the next case is something where we talk about circular polarization, remember? Remember there are two types, it's right or left hand, correct? Just work with me on this one, exhausted or not. So now I'm gonna let the phase angle be equal to pi over 2. I wanna make it, get rid of that. Make it plus pi over 2. It could be minus. All right, now let's go through this one together. I'm gonna plot the EX component in EY versus time, points. Here's EX, here's EY. All right, omega t is 0, right? Everybody with me? So start omega t is 0, EX would be E0. Do you agree with this, everyone? So come over here and I put E0 down. You can just use 1 because typically I make that 1 to make it easy. Now what's EY? Well, it would be the cosine of 0 plus pi over 2, which is 90, right? What's the cosine of 90? 0. So EY is 0, right? That means the entire vector, the superposition of these two, is right here. I'm going to show you. That's the electric field's hand, if you will, at t equals 0. With me? Let's do the next point. Now let omega t be equal to pi over, I'll tell you what, yeah, we'll go pi over 4. What happens up here? Cosine is pi over 4 is 1 over square root of 2, right? So this one, the value on this axis comes down to here to 70%. What about the vertical value, EY? Now I have cosine of what? 135, don't I? What's the cosine of 135? We're past the null, past the 0 point, right? It's negative, right? It's negative 1 over square root of 2, isn't it? So it's down here. So here's the next point, right here. All right, by the way, the magnitude will be 1. If you take a look at this, it's 1 over square root of 2 plus 1 over square root of 2. If you're talking about two orthogonal components, square both, you get 1/2 plus 1/2 is 1, square root of 1 is 1. So the magnitude is 1. And what you can see, if you just take this out, so omega t is 90, that the hands of this clock are turning this way. Same magnitude, it'll be a circle, but now it's going like this. Now look, the direction of propagation is z, right? So is that left hand or right hand? That would be right hand if it was going that way. Is it going that way? Take your left hand. Is it going that way? Yes, this is left hand circular polarization. The way you determine it is plot a few points. That's the best possible way. There's all sorts of rules, Wentworth's got this book. Don't ever worry about that. Just plot 2 or 3 points, you figure it out just by looking. Right? Remember, you got your right hand, left hand, both. You all have them. And we use those to determine the direction of propagation. Just point your top thumb there, and if it turns this way, it's left. If it turns that way, it's right. E-field moves out. So that's basically circular polarization. What do you think? I mean, I can make elliptical polarization a whole lot of different ways. Instead of making this pi over, and I can get it going the opposite direction if I do this. If I just make that angle minus, now it becomes right hand. You all follow me on that? There are other ways. There's a whole variety of ways to mathematically get what you want to observe. You just have to understand how to actually identify it. Plot a few points. That's the easiest way. Now, here's something. If I wanted to make it elliptical, can you think of what you could do to these two basic formulas? What would be one obvious way of making it elliptical?
Change the magnitude.
Sure, I could make this magnitude 2 E0, right? And then it would definitely be ellipse, correct? Absolutely. Anything else I can do? Suppose I wanted the elliptical axis, not the major axis, on either the vertical or horizontal direction. What if I made this phase angle be pi over 4? That will cause an ellipse to form, even if the magnitudes are the same. Y'all follow me? And the only way you can tell which way the ellipse's hands are moving is plot a few points. But my real point is this. These are only mathematical descriptions to allow you to define polarized waves. It's nothing magic about this thing. The real usefulness of this comes later on in radar and signal processing work, where you're trying to identify targets. You sent this waveform out, I received this waveform. I do polarization filters based on time delay and correlation. I can figure out where the target is, and how fast it's moving. I can get Doppler shifted. We did Doppler, right? No, we didn't do Doppler, never mind, sorry, wrong class. Anyway, you'll learn about that in EMAG too. Okay. I was gonna do a reflection, but I'm gonna stop there. That was Friday's polarization lecture, and I'll give you your quiz. So, would you do me a favor?